We're talking about creating evolutionary design and architecture. We are in part 3. Let's talk a little bit more about how to approach creating evolutionary design. We talked about the reasons to do it. We talked about some of the ways to approach it, like keeping it simple. We talked about refactoring, quite a bit about reversibility and last responsible moment. But let's switch our focus to something that shouldn't be done in the first place. Peter Drucker said, there's no point doing efficiently what shouldn't be done in the first place. So this comes to what's called the Yagni principle. This is one of my favorite principles. The Yagni principle stands for you aren't going to need it. So you aren't going to need it. And the problem with this particular approach is that people get a little apprehensive when you say you're not going to need it. But I normally add the word yet to it. You aren't going to need it yet. So that at least appeases people a little bit and saying, you don't need it now, we can postpone it, and then maybe if we really need it, we can implement it. Well, the Yagni principle is simply saying that you don't really need certain things and you can avoid really implementing it. And when you develop application, we normally create so much fluff around it, perceiving that we really need it, but we actually end up really not needing it. I often, when I create applications, I come up with a massive set of ideas from the domain model. Here are classes, here are the relationship between them. And once I draw a UML diagram of all of that, I look at this and say, dear Lord, this cannot be true. Does this application really need that many classes to really implement it? And I'm a person who tries to keep things as simple as I can. I'm not perfect. I'm struggling as much as anybody else is struggling. But one of the things I really strive to do is to keep things very minimum. And I say to myself, I can postpone implementing this. And if I can avoid implementing it, it's even better. Now, you go to a programmer who has written a piece of code 2 days ago, and you tell the programmer you don't need it, get rid of it. You're probably going to get a lot of resistance from the programmer. Not all of them, but most of them would probably resist to you. And the reason is they're putting so much time and effort building it, and the fact that you're going to throw it away becomes really problematic. But if you go to a programmer and say, remember you were going to implement this particular class in the UML diagram? You don't need it. Oh, what a relief. I don't have to implement that piece of nonsense, right? So the point really is, when you are building application, try to see if you are not going to need it yet. So as I am working through tactical design, or even at the architectural level about a messaging component or a tier, I ask myself, do I really need this right now? If I don't need this right now, I'm going to postpone it, and eventually I see that most of the things are working and I still haven't implemented this class or the component. Hey, maybe I don't really need it, and I can just get rid of it. So in other words, you aren't going to need it. This comes to methods, classes, member variables, state. I can't tell you how many times people build state into applications when that state is really not necessary. So try as much as possible to get rid of stuff or at least postpone, so we actually end up building only things that are absolutely important, things that we cannot live without. That is extremely important. So when creating a class, hey, what if I really don't need this class? Maybe I can use a simpler representation of this class for now. Then I could get away with it. Or, hey, I need this class, but I really don't need this class at this moment. I only need this particular property of this class. Maybe I can represent that as a field in this current class. Or maybe I can refactor this into a separate class later on, because that's when I really need that abstraction, but not yet. So when it comes to applying the Yagni principle, why do we eagerly implement code most of the time? Because for one, well, we decided this is the architecture, this is the design, we got to implement it, right? That's one reason. But the other reason is we are anxious. We are eager to put stuff together. As we are writing code, oh, I got to handle this other condition, I got to handle this other condition. I'll give you, this is a very tactical level, but I'll give you an example. I was pairing with a developer once, and as we were writing tests and writing code, as I was in the middle of writing a piece of code, I said to myself, oh, I need to handle this other condition of this boundary, isn't it? And plop, I immediately write the code. The gentleman sitting next to me elbows me and says, hey, aren't you supposed to write a test for that before you write that code? Oh, yeah, you know what, you're right. So on the task list, check for this boundary, removed the code I wrote, went on, finished, every test is passing now. Then we wrote a test that says check for this boundary, and to my surprise, to both of our surprise, the test actually passed. Now we looked into seeing why the test passed, and it turns out that the language actually handled this particular condition already, and we didn't have to write an extra piece of code to handle it. That code I had written is completely unnecessary. I was not going to need it, but I would have typically written it. Likewise, how many times are you going about initializing a massive data structure when that's the default initialization in the first place? How many times have you created classes that is not really needed, and yet you created it because we thought about it during the design phase, and so we want to go ahead and create it? So when it comes to the Yagni principle, apply some of the logic we can. Think of the cost. Let's say the cost of developing now is $1 now. Let's say the cost of developing later is $1 later. Now, what if the cost of developing now, this particular feature, let's say we have a couple of different options, right? What if the cost of developing now is a lot greater than the cost of developing it later? Now you may wonder, how in the world is it possible for the cost to be less tomorrow than now? Well, that's quite possible. It's possible that we have developed other little features, and maybe using those we can actually build this particular one, so we don't have to expend all the effort in building it possibly. So that's one option. The second option is the cost of building it now is equal to the cost of building it later. That's a second option. A third option that may be possible is that the cost of building it now is a lot less than the cost of building it later. Well, if you have a hunch about this cost, if it is more expensive to build now than to build it later, then postpone, because it is a lot more cheaper to build it later than building it now. What if the cost of building it is the same than building it now or building it later? Well, then what you need to really think about is, maybe in this case also we should postpone. Why is that? Because if the cost is going to be the same, you might as well build it when you have more context, more knowledge, and more information, and you can focus on one that has reached the last responsible moment. That one can wait later, so postpone it. And if the cost of building it now is a lot less than the cost of building it later, then ask a few other questions. What is the probability that you would really need it? If the probability of you really needing it is very, very high, go ahead and build it now. If the probability is relatively less, or if you are unsure, it's much better to pay that little extra cost and build it later than to build it now. And so as a result, the Yagni principle is, again, I usually introduce the word yet just to appease myself and others, to say you're not going to need it yet. Postpone the decision, and if you really need it later on, you can build it at that time, but you don't have to really take on that at this moment right now. So that is something to think about when it comes to how can I really postpone those decisions and eventually figure out there are certain things that don't need to be implemented at all. And I've quite a bit seen some of these things along the way where I've realized that some things I needed to implement, I realized I really didn't need to after all. I was misconceived in my notions and my assumptions, but I can implement it very differently. And when classes that I had to write simply disappear, that is so rewarding. And the reason for that is, hands down, the code you did not write has the fewest bugs in it. So it's better to really postpone those decisions and avoid writing it, and only develop minimum code that actually meets the expectation of the application and delivers value. Well, okay, that's great, but we got a little architectural vision on in front of us. But how do we go about implementing this? What are the approaches we can take? One approach is called the tracer bullet approach. The idea behind tracer bullet is, this goes to the connotation of guns. When people are going to hunting, you could try to fire at a target. Well, if the target is pretty static, you're trying to fire at an apple, for example, that's on a tree when there's no wind, well, you could probably get really good at it with enough practice. But what if you're trying to fire at a moving target? And what if you are moving and the target is moving at the same time? So the point really is that tracer bullet approach is where there's a tracer bullet, a laser little thing that actually the bullets actually have a little bit of a phosphorus material, whatever material they use. And so it, like a laser beam, it shows you a little trajectory through this material as these bullets are fired. So in the rounded bullets, every few bullets have a little bit of these coating. So when you start firing, it shows you a trajectory like a laser view, but not quite laser, but these views through these bullets, material in the bullet that shines through and shows you where things are. Well, the point really is you could do all the math and all the calculation you want, and there are times when that's the right thing to do, like trying to fire a missile. But in other lot of different cases, this trajectory gives a very quick feedback loop. Our eyes see where the bullets are going, and as a result, immediately our mind can process that, and then we can realign, and so that's a tracer bullet. But the idea really is to really do something, experiment, and use the feedback loop to go back and evolve it. So let's think about an example of this in a physical world, and then talk about how this would be in software. Let's imagine that I'm going to be moving into a new office room. My office room, I know the dimensions for my office. It's located in another city that I'm relocating to, but I've got certain furnitures in my office. These are pretty heavy furnitures, and of course the moving company is going to move it, and when they move it, I want to tell exactly where to place these. So I go to my new office, which is pretty empty room, or maybe I don't even have access to my office, but I know the dimensions of my office. So what can I do? Either I can go to the office it's available, which is empty, or I can find a big room and I can draw on the floor the dimension of the room and say, this is the space available to me. Now I can do a few things. I can sit or stand in that area, open area. I can visualize, but more than visualizing, I can bring cardboard boxes that are the dimension of my furnitures, which are pretty heavy, but the boxes are relatively lightweight. And I can place these boxes in various places in the room, move them around, and get a feel for it. Would I want the furniture to be here? Would I want my desk to be here? Would I want my printer to be here? I can put these and arrange them, and I can get a visual feel for how things would look like. I can move things around and say, I like this better. Or, oh, I'm a person who cares about a lot of open space, and I want area to walk around, to pace around. So if you look at my work areas and the places where I normally hang around, they have a lot of empty space for me to walk around, and I normally keep things away. And as a result, I can put things and say, would this meet my expectations? A colleague of mine may have a completely different expectations and views and liking, and they can try out in a similar way. But once we do, we can then jot it down and say, hey, moving company, this is exactly where I want my stuff to be laid out, and this thing should go here and here and here. I can mark it down so the heavy furniture, they can move and I don't have to struggle with it. So the idea really is we create these mocks, not mocks from the point of view of testing, but from the point of view of getting a feel for whether these are the things we really want in place. And by creating this architectural vision, when you start implementing the feature, you don't have to implement an architectural component to the full extent. You can implement just enough and sometimes even fake away. So in the beginning, you could use an in-memory database, for example. Sure, if you close the application, the data is lost, but hey, during initial development, the first couple of sprints, who cares? So you can enter some data, play with it, and you can load some sample data into the memory and play with it. You don't need to have a real database. So the point is you could really come up with all these different mocks, run the code through, and see if these things fit together. And if something doesn't quite fit, or if the needs are very different than what you perceived in the beginning, you can alter them, and in the process you evolve your architecture, and that's essentially the idea. So the tracer bullet approach really is to really mock away as many parts as you can, provide fake implementations, and then using that fake implementation, slowly evolve and replace those fake implementations with real ones, and that real one would really serve the purposes of the application rather than brute force implemented based on our original vision and ideas. And that is something we can try to develop as much as possible. And in other words, we try to create something and play with it and see if it really fits, and then we lock it in. In a way, I'll give you an example of what I learned when I was a child. My dad taught me how to do these things. If you're trying to build a little, let's say you're trying to put together a little drawer, for example, or a cabinet. One thing you don't do is you don't start tightening every single piece of screw and say, I'm going to get this tightened. One of the things you do is you tighten them just enough, but there is enough wiggle space, and then you put them to a shape, and when things are a little wobbly but they are put into shape, then you start tightening, and then it locks in. And the reason is if you tighten every single one of them, you get into a misalignment very quickly, and then you realize that it's bent out of shape. The same thing with software as well. You don't try to tighten things right in the beginning. You put together and you kind of evolve it and see if things align and work together. If they don't, then you realize this is not the right interface or a service you wanted to use. Replace that with what is more serving your purpose. And then once you have things working, eventually it snaps into place as you build more things on it, and slowly the fake things and the mock things you create transforms into the real code and evolves properly. Now, one other holy grail in our development is extensibility. Now, we all want to create software that's extensible. But how do we really create software that's extensible? Well, the very first problem is, what is extensibility? Well, you first of all want to definitely create software that's extensible. Now, how do you really make software extensible? I'll talk about two separate things here. Well, I'll tell you one way it's very difficult to extend software. If you create a software where you have rigid team boundaries based on your architectural layers, you have a DB team, and you have a service team, you have a security team, and you have a team that's going to be in charge of, whatever the service is that you're going to provide. And so when you have these different teams, what happens? When you have to build a particular feature, you have to really send this message across to these teams and say, you guys implement this, you guys implement this, you guys implement this. It becomes unbearable to communicate between these teams. And extensibility is very difficult when you have these teams that are taking ownership of different parts of the project. And then what happens? In fact, I know quite a bit of companies where this is a very common problem. A particular application requires all these different services, but these are very politically managed to different teams. And as an application manager, this person has to send out the requirements and wait for all these teams to implement. And the time they come back together and integrate is when everything goes up in flames. And very difficult to extend software in this case. When a new feature has to be added, it takes months and months to add a new feature. Why? Because you got to really drill it down to what that means to each of these teams and send it off these teams and wait for them to implement and then come back again. Integration goes up into flames and it becomes extremely difficult to coordinate. So if you really want good extensibility, the first place to start looking at is not the technology, but the first place to look is how your teams are organized. If the teams are organized across a technology stack, that is a big disadvantage. Don't get me wrong, that's the way a lot of companies do, but that's where the problem comes in as well, that it increases the cost of development when teams organize that way. But what if, sure, there are times when you really need these kinds of teams, but what if you have a cross-functional team where your project has people committed to your project, but they got access to these different layers, and somebody could be coordinating through those layers, but these people actually have, and they can collaborate more easily, and try to figure out how you can reorganize your teams so that it is faster to extend your application. If the way your organization is structured in a way that extensibility becomes really hard because of the way humans communicate with each other and how the change goes through and how integration happens, the first place to make the change is in the organization, not as much in the technology itself. But when it comes to technology, what about extensibility? I was talking to a team, and the manager of the team, we had the entire team at lunch, and the manager said, every single day my team told me the product is extensible. Every single day they will tell me they're building it for extensibility. And once we deployed the product, we got one single change, which required just a very small change to the application. And my team said it will take a few weeks to make the change. And so he asked me, what's up with this? Why do you think this happened? I told him, it's your problem. You are wrong. It's your problem. He said, what did I do wrong? I said, the software was extensible until you asked it to be extended. So the point really is, a software is extensible until you want it to be extended, meaning that we can perceive that, oh, my software is extensible, but how do you know it's extensible until you actually extend it? And this is where the problem comes in, is we build all this structure and hierarchy, like Ralph Johnson said, and when the extensibility comes through, it becomes cost prohibitive. Now, one reason why extensibility becomes really hard is that we often end up violating this principle called the DRY principle. DRY principle stands for don't repeat yourself. So, don't repeat yourself simply says that in your system, you don't want to really have decisions being made at multiple different levels. Now, DRY is not duplication of code, it's duplication of effort. Now, how many times have we seen where we get a little change request, and to make this change, we got to change the database schema, we got to change the models, we got to change the controllers, we got to change the view, we got to change the service component, we got to change this XML formatting, and by the time we are done, we are touched about 7 different places to make this change. That's an example of the DRY principle being violated. So, in other words, if we can minimize the impact of change, it would be a lot better and easier to make the code extensible, and that is something to keep in mind as well. So, okay, that's great, we want to make the code extensible, but how do we really make it extensible? Does it mean we create a hierarchy and interface a class and start deriving things? Well, not really. Because one of the disadvantages is, if we start creating a class hierarchy in the beginning, we end up with a monstrous code. I once came across an application where I went to this company, they asked me to do a code review, and as I started doing the code review, I found out quickly that they had so many interfaces. And they had so many interfaces, when I looked up a little bit further, I saw so many interfaces that never had a class implementing it. And there were several other interfaces which had exactly one class ever implementing. And I went around and asked them, I don't understand this. How come all these interfaces have no classes at all implementing them, and these interfaces have only one class? What's going on here? And they said, oh, the guys who wrote the code don't work here anymore, but they set out to create a framework and ended up just delivering this application and walked away. We didn't have time to finish it. Well, that's one of the problems. We try to make things way too extensible than they should be. Ken Beck talks about this approach called triangulation. Triangulation really is that when you are thinking of a particular abstraction, sure, in your architecture, you may say, here is a component that could be implemented in different versions. Here's a component, for example, that's got to talk to Twitter. Here's a component that's got to talk to Facebook. Here's a component that's got to talk to other social media. That's perfectly fine, which means that there's abstraction of this component. Or you may say, well, here's a class, but this class could have different types of implementation. I need an interface for it. But don't start by creating an interface. Instead, simply create a class, let's say class 1. Go ahead and create this class. And once you create this class, get your code and test working with it. And a few weeks goes by, maybe a few features go by, and you come up across this other feature where you need this other implementation. Go ahead and write the class 2 at this point and implement the class 2 just now, because you realize you need to implement this class 2. Sure, there will be a little bit of duplication between these two. Go ahead and do that. But once you have this class 2 implemented, now you know whether class 2 really is very similar to class 1, except for these areas of difference. And if there is enough commonality between class 1 and class 2, then and only then extract out the base class from the commonality and take what's common between class 1 and class 2, move it to the base, either an interface or a class or a combination thereof, and then inherit class 1 and class 2 from the base. So you write this first, that is step number 1. Then you implement this is step number 2. And the third step is to pull what's common up into the base. That's triangulation. So you start out here, you implement this, and then you take the common and you triangulate from these 2 points, and that's where the triangulation concept comes in. So when it comes to building a hierarchy, do not start with the hierarchy, but end with the hierarchy. If you start with the hierarchy, you possibly have a monster and complexity. If you end with the hierarchy, that hierarchy is very practical and serves your need. If you realize that this base is not really needed, you wouldn't create it. If you feel that the base needs only these minimum things, then your base is going to be really minimum, and the derived classes can do their own stuff that they need to do. So that's a better way to do it. Well, another holy grail in our development is reuse. Almost everybody, nobody wants to create something that's usable, they want to create something that's reusable. Grady Booch once said, first create something that's usable, then create something reusable. Well, when it comes to creating components, we want to create something very reusable. But think about this for a minute. If something is usable, it has to be very, very direct and specific, right? So for you to be able to use something, it has to be specific. But for something to be reusable, it has to be general enough, right? So it's got to be general enough for being reusable. So reuse requires generalization, and a use requires something to be very specific. There's a bit of a tension between these two. You can make something very specific, or you can make it so general that's not really usable, but it's hypothetically reusable. So how do you really create something that's really reusable? There's actually good ways to do this. Let's look at some examples of this. When certain technologies were created, like for example, the original versions of EJB, or when EJB was created, they had MTS, Microsoft had Microsoft Transaction Services, and the Java folks said, oh, we got to create an EJB. Why are you creating an EJB? Does the world need EJB? No, we got to create a framework. So they created something absolutely reusable, but it failed in so many ways. It was heavyweight, hard to use, and most problems did not really need it, but people had infatuation of technology, so they ended up using it. But how do you really create something that is really reusable? Well, start by using it. A great example of this is Spring. Rod Johnson said, you know what, this EJB stuff is too heavyweight. All I need is something very, very simple and lightweight. He started putting together a hodgepodge of Java classes, what he called as POJOs, or plain old Java objects, and started building with these POJOs, and then said, hey, this seems to do what I want to do in this particular project. Here's a second project. Oh, I can carry over this as a library, and I can make changes, and he refactored it. And a few projects later, he had something that's very reusable. Same example is Rails. Rails was not created as a framework. It was extracted out, refactored out of implementations that came about from several different projects. So successful libraries and frameworks did not come from creating a library or framework. They came from application and use and extraction from it. I'm a huge fan of standardization. So standardization is extremely important. I cannot argue with that at all. But to me, innovation is also extremely important. And if we disregard innovation and only focus on standardization, we are in real trouble. So to me, standardization is important, but don't be too quick in standardizing, creating a library or a framework. So innovate and then standardize. So standardization after innovation is extremely important rather than the other way around. So innovate, implement on several projects. Whatever is common, refactor it, and when it gathers enough mass around it and see that it's been used and used and used and used, and it's been reused, now you got a library or a framework that can be reusable. So don't start out to create something reusable, Start something that is usable and use it several times, and then extract something that's reusable from it. I once worked in a company where they wanted to take components that were developed in several products and they wanted to create a reusable component. The VP had this a vision that he wanted to create something very reusable. It took them 12 years to extract that component in a reusable manner, because using it in different projects was easy, but when you create one component that's reusable, you got to make it so general that it can be reused widely, but so specific that it actually is usable in these different contexts. Not a very easy thing to do. Likewise, we have to also keep in mind about a few other things, which is about parsimony and how that can influence the library creations and usage of libraries as well. But we'll talk about that in the next part of this presentation.